I'm Bill Mall, and my guest today is Albert Pitt Shepard, but we're going to call you Pete Shepard, if we
Please
may,
do.
Dr. Shepard. Dr. Shepard is a retired professor of physiology from UT Health San Antonio, but he launched the Avox systems back in 1976, and we're going to go into some depth in understanding that today. It's a company that has been built in a solid state, I'm going to say this, arteriovenous oxygen difference analyzer. I can say the words, but I don't have a clue what it is or does, so you can help us understand that, please.
Well, I'll have to go back a ways in my history. I was born and raised in Mississippi, and when it came time for me to go to college, I knew this was going to be quite a challenge because my parents couldn't afford to send me, and I would have to have jobs part-time and summertime in order to go to college. I chose Millsaps College because it had a great reputation for academic standards. Now, what I didn't know when I chose Millsaps was it was just across the street from the University of Mississippi Medical Center, and there was probably more research going on in that institution than anywhere else in the whole state of Mississippi. So I managed to get a part-time job there, and as it turned out, it was initially in sort of a clinical chemistry department, but actually I was part of a research team, and we ended up going to Colorado and trapping wild mice, and my job was to catch the mice, go and check the traps, catch the mice, take blood samples from them.
These were have-a-heart traps, I take it.
They were homemade traps, but the animals were alive.
Right.
And after that, I got my first publication, and it was about hemoglobin in these mice that lived at different altitudes.
And you were collecting the mice, and that intrigued you enough to write the paper about the elevation effect on blood?
No, the head of that research group did, but I was one of the authors of it.
I understand.
Now, that job came to an end, and the next job I found was in the Department of Physiology. Now, even before I found any kind of job over there at the medical center, I knew who Arthur Guyton was. He was world famous for his cardiovascular research and for writing what's one of the best-selling medical textbooks in history. So I got my job over there in his department.
So you were the lab technician in this case?
Yeah, exactly. Now, as I said, many people knew that Guyton was famous for those two reasons. Almost nobody knew that he was a businessman. And he invented first arteriovenous oxygen difference analyzer.
And what was the purpose of it? What does it do?
Well, again, now remember, all of this was for experiments on anesthetized animals. And if you wanted, for example, to determine the rate at which an organ was consuming oxygen, you could use something like an electromagnetic flow probe to measure the blood flow. And if you sent the blood from the animal, say from the artery, through one of these, a cuvette similar to these, the blood would flow into his instrument and back into the animal. And then you did the same thing with the venous blood from the organ in which you wanted to measure oxygen consumption, and it went back into the animal, and it gave you a continuous measurement.
Now this was for veterinary science, was it?
No,
This
quite,
was for
quite
human
a bit
beings?
of what we know today that pertains to how the human body works was based on animal experiments. It really was. I spent most of my career using anesthetized dogs. They were going to be put out down at the pound anyway. They died actually in a very easy way. They just simply were put to sleep,
Right.
never woke up again. That was it. So Guyton had this AV oxygen difference analyzer, and I used it in the experiments that went into my dissertation. Now, after that, I did a postdoc at the brand new University of Texas Medical Center in Houston. They didn't even have a building in 1971. And there is where I started studying the control of blood flow in intestine. and I convinced them to buy one of Guyton's AV oxygen difference analyzers, if you want to call it that.
So, Dr. Shepard, you took a lot of knowledge from Dr. Guyton, who had written the book and who was so knowledgeable about this. What did you learn from him that applied to this first AV analyzer?
Well, I learned that you could be an academician and a businessman at the same time if your institution didn't prohibit you from doing that, and it didn't in Mississippi.
A good thing.
And I also learned that even a genius like Guyton could be very stubborn. Now, although I bought his instrument when I got to Houston, I bought another instrument when I joined the faculty at the University of California in Irvine, and when I moved to San Antonio, I bought another one. So I became one of Guyton's customers.
One of his biggest customers, apparently.
Probably so. Now, I use that instrument quite a bit, and I am indebted to him for giving me something that I could use in my research all those years. But even in the 1960s, when I was a graduate student, that AV difference analyzer of his was an old contraption.
It was a big device, wasn't it?
Well, it wasn't too big. It was about like a case like that you see over there.
So about a foot or 2 feet in
something like that.
dimension.
But it was really an antique in the sense that it had vacuum tubes and light bulbs and moving parts, not transistors and that kind of thing, LEDs. And so
it was developed in the early 70s, is that correct?
No, his was probably in the 50s, and I was there as a graduate student in the mid-60s. So even then, it was out of date. And so one of the things I did here was I managed, to get a grant to study blood flow and oxygenation of the intestine and so forth. And then on the side there, I was working on a way to design a new AV oxygen difference analyzer that would be better than Guyton's.
And how did you do that? What did you do that made the difference and improved the product?
Well,
what were the key features, I guess?
His was slow. It was heavy. It tended to break down. Things like that. Mm-hmm. And I knew that if I could just find an electrical engineer, I had the main components in my hand. I had found everything I needed to build a better one, but I needed somebody who knew how to put them together.
And what were those main components that the engineer helped you put together?
Well, one experience I had early on, I think I went to a physiology meeting in about 1961, and there was a guy there who was good at electronic designs, despite the fact that he was an MD. He was a wizard with the designs, and I said, "You're familiar with Guyton's old contraption. How would you redesign it?" And he said, "Well, if I was going to do it, I'd use LEDs." And I said, "What is an LED?" I never heard of such a thing. So
a light-emitting diode.
Yeah, of course.
In what year?
Probably 71.
Yeah. So it was still emerging technology.
Yeah, it was not something that was well known, but he knew about it. And then when I got here, I started looking for someone who could help me. And
got here to the University of Texas.
Anywhere I could find him. And I already had what they called a log ratio module. Part of the Beer's law requires you taking logarithms of intensities and things. I had a device that would do that. I had the LEDs. I had the light detectors. I had the major components, but I couldn't get anybody to help me. Now, there was a fellow in the physiology department who sort of knew the local engineers. He sent me to Trinity, and I gave a seminar and told them how I needed to do this. And they said, "No, thanks, we can't do that." And then I got some people from Southwest Research to come over, and they said, "Guarantee you, we can do you a prototype. It'll only cost you $200,000.
So you opened your wallet.
That'd be about $1 million in today's currencies,
So funding was.
But let me finish that one.
Yes.
The same fellow who was saying, "Try them, try them, try them," he said, "Well, there is another possibility, but I kind of held back on mentioning that. There is an electrical engineer working in the psychiatry department as a technician. That was Chuck Berger." And so it was Chuck Berger and I who, not this one, I'm sorry. who
The first
developed the
prototype.
first arterial venous oxygen difference analyzer to supersede guidance.
And who bought it?
Scientists like myself.
And you had to learn a little something about marketing about that time, didn't you?
Yeah, and in fact, when we got the company started, because it was used for the same kind of research that I did, it wasn't too hard to find a potential customer. What I had to do in those days was go to the library and find a professional librarian to do a literature search for me. And when she gave me a list of all the publications in a given year in which the oxygen consumption rate was measured in some animal, then I would send a letter to that author, and it would cite his, the bibliographic information. So I knew about his article, congratulating him on his excellent research, and point out that it could have been done a lot easier if he'd had mine.
Now, you learned something fundamental about direct marketing, highly targeted direct marketing.
Yeah,
And it was effective for you.
yeah, it worked for that.
And you were targeting cath labs early on, too, were you not?
Well, we'll get around to that
Okay.
later. But when it came to the old AV oxygen difference analyzer, it was essentially researchers like myself publishing papers in journals I was familiar with and so forth, and the direct mail advertising to them worked. Now, what was more difficult was selling it in other countries. And we never sold these in huge quantities. I think the best year we ever had was 2 dozen. But if you're running a garage shop, your overhead's pretty low. And so the three of us, my research associate, Greg, and the engineer and I, had that business.
Chuck.
And it was, Chuck, and it was profitable all that time.
But for you, it was a sideline. This was not your key
Oh, yeah.
focus. You were
Yeah.
a faculty member teaching.
Yeah. And at the same time, as a businessman, I managed to get a distributor in Germany and one in Japan, and I literally did manage to get these things all over the world. Now, a colleague of mine, a former graduate student with me, he said to me one day, Pete, I like the research you do, on blood flow in the GI tract and all, but I think it's great you're giving tools to other investigators to do their research. I hadn't even thought about it that way.
So it was a benefit that went far beyond just analyzing the oxygen for you, a side benefit, an unanticipated benefit.
It was helping other investigators measure the oxygen consumption rate of various organs and so forth. And so it was a gratifying thing, and it was a little, garage shop.
Now, did you envision in those early days that this device would turn into the kind of device that it has, that it's become a global tool for just this kind of analysis and investigation?
We actually invented it by accident. I didn't anticipate anything like this.
So much of invention is serendipity, isn't it?
Yeah. Now, if I could go back a little bit, I told you I was in Irvine 1 year, and at that point, I was already thoroughly familiar with guidance device, and one of my colleagues, John Sutherland, was quite a physicist. So we borrowed a contraption called a dual beam absorbance monitor and ran blood through it. It wasn't made for that, but we found out it could make the same measurement as guidance did, but it really wasn't fit for the lab work.
Mm-hmm.
But what I learned from him was that the optical properties of blood are just incredibly complicated. Now, because he was a physicist, he could do things like say, okay, I like the data you got, take the reciprocal of this and the reciprocal of that and plot it again and show me what you get.
Did you know how to do that?
I could do that, but the lesson he taught me was the optical properties of blood are very complicated. And so when I got here and got my instrument going, I could prove it worked, even though I didn't completely understand how it did. Now, one event that I'll never forget that changed the rest of my career was when a colleague from biochemistry came to my lab. He had a young fellow with him. He said, "This is John Steinke. He just finished his first year at Rice, and he's looking for a summer job. Can you keep him busy this summer?" I kept him busy for 22 years. Now, it's absolutely accurate to say John Steinke was a mathematical genius and exactly what I needed to figure out how my old AV difference analyzer worked. So that was the first job I gave him. Now, the other thing was that John and his family were both just extremely religious. His family, his parents had sold the family farm in Iowa and moved to San Antonio in the 70s in order to stay with the same preacher.
Uh-huh.
The same preacher. John had this same thing. Because of that, he wanted to be in San Antonio with his family and that preacher as much as he could. And so the whole time he went to Rice, even while he was at Princeton getting his PhD in mathematics, he worked in my lab not only in the summers, but in the holidays. I can remember one time when we sat down and designed a study, performed the experiments, analyzed the data, and wrote the first draft of the manuscript in the Christmas holidays.
And he was one of the three people who are responsible for this invention. You,
well, it's
John.
The two of us for this one, the clinical one.
Mm-hmm.
We are the two who are responsible for that. But in the case of the old thing like the AV difference analyzer, that was more or less me and
your engineer, Chuck.
Yeah, my engineer, Chuck, the engineer.
Yeah.
I'm still in touch with Chuck too.
That is a good thing. Are you still
Yeah.
inventing with Chuck?
No, actually, he was a technician in the psychiatry department, putting together devices that sort of would monitor patients and all. And he later went to medical school here. He got some money to help him through medical school from Avox Systems. I had him at work.
Now this is the 1000, but you've had other iterations of it. Can you tell us about how the iterations of the Avox have come about?
Well, let's see. As I mentioned, one of the things I wanted John Steinke to do was to figure out how the old AV difference analyzer worked, the one like Guyton's. And so the first two papers we published were about how Guyton's AV difference analyzer and my AV difference analyzer worked, and another paper that same year about how the oxygen measuring ones, the oximeters, work. So we started off just saying we can explain how those instruments work. Even though they've been used for years, this is how they really work, and this is the role that light scattering plays and the role that optical absorbance plays. And so the main thing I wanted to do was just to understand that, and that's what Steinke helped me do. Now, after that, we started tinkering around, and I always liked coming up with gadgets that I could use for my research. And I just did a quick look at my publications, and I remember when I got my first graduate student in the mid-'80s, the first job I gave him was to turn an Apple II computer into an oximeter and an AV difference analyzer.
And he did.
Yeah. And then there were other gadgets in my bibliography, a drop counting flow meter, a reflectance measurement hematochritometer, or whatever they call it. I did publish a lot of things about gadgets that I wanted for my own use. And we really weren't focused on developing a clinical product. Now, as I told you, John worked for me every summer and during the holidays. And well before he graduated Princeton, he came in at the end of one summer and showed me his data and said, are we going to write another paper? And I said, absolutely not. We're going to write a patent application. We had discovered something.
So you knew then that it was ready to be patentable and marketed.
Yeah, and what happened was when I was developing my old AV difference analyzer in the next building over, I went over to the hospital, which has had 4 or 5 different names in the last 40 years, and got to know the people in the so-called blood gas lab. They have a lab close to the operating room, so they can run down there with samples and analyze them and go back and tell the anesthesiologist, what's going on. And I got to know both the people and the instruments they were using. That was the key. That was when John showed me his data that I realized we had stumbled into a new invention. And really all it was all of the so-called co-oximeters that were being used in hospitals all over had to first rupture the red blood cells to get rid of the light scattering that they cause. Now, if you shine light through blood, some of it gets absorbed and it more or less obeys Beer's law, but the refractive index of the contents of the red cell are different from the refractive index of the plasma around it. So when light comes through, it might go zooming off at some angle and not get to the detector. Well, what all of those companies had done is come up with a way to suck up the blood, run it through some pump, and rupture the red blood cells either chemically or with an ultrasound thing. Now, once they were ruptured and got rid of the light scattering, they could make the measurements. John had been fiddling around saying, how about if I add another wavelength? How about if I try some more? Well, he liked to see it when you had all these multiple simultaneous equations, and that's what you were actually doing when you were trying to figure out the percentages of the four main species of hemoglobin. You had to have those four Beer's law equations, and with four equations you can solve for four unknowns. He said, how about we throw in a few more wavelengths and have some more equations?
Talking about refraction, I think you had some really serious problems with the cuvettes refracting light, and you had to understand those light frequencies in order to create a better cuvette, did you not?
No, that was not the problem. What we had learned, from the data that John showed me, was that if we had the right optical path length, we could get the concentrations of the four major species and the total hemoglobin. But it required a fairly short optical path length to minimize the scattering. The further the light goes through the blood, the more it zigs and zags and goes all over the place. So it needed to be fairly thin, about 100 micrometers. Now, I never will forget, I was lying in bed one night thinking about how we would do this, and what I thought of was this. If you look at this, this is a sandwich. It's two pieces of clear plastic held together by a two-sided adhesive tape. That's it.
Pretty simple technology.
Yeah.
Not complicated.
Now, here was the thing that amounted to. I had hoped that the optical path lengths would not vary very much. That the tape would be the same thickness and they would all be the same optical path length and everything. And they were fairly consistent. Now, what that meant from a functional point of view is we could, even the way I dreamed it up that night, measure the relative concentrations of the four main species of hemoglobin in that cuvette.
But not necessarily.
No, but the total hemoglobin concentration, is in absolute units, grams per deciliter sort of thing. The other ones are just percentages, no units. So we couldn't measure the total. Well, I was headed on one of my trips to Europe one time, and I told John, why don't you try shining a laser beam through here and see if you can get it to reflect off the internal surfaces. See, that's an empty cavity in there.
Yes.
See if they can get the light to reflect off that, and maybe the angles of reflection will tell you what the path length is. So that was the task I gave him when I took off for Germany.
And he solved it.
No, he didn't. What I was suggesting didn't work. And he called someone out at Southwest Research and told him about it, and the guy immediately said, try measuring such and such, a reflectance pattern. I can't remember what the technical term was. Try measuring that. And I finished giving my seminar in Berlin and borrowed the phone and called home and said, how's it going, John? And he said, told me what the fellow at Southwest Research recommended, and he said, I think I've already got a little device built that will measure the optical path length inside that cuvette. And what that means is, even if we can't manufacture them so the optical path lengths are exactly the same, we can measure it without putting anything in it and sort them. And so what we did for the whole history of this instrument and the Model 4000 was we'd sell a bag of cuvettes, and there would be an optical path length on it. And of course, the instructions said, when you get a new bag, put in the optical path length for that bag. that's what we did.
And the benefit from the 1,000 to the 4,000, what are the benefits that have served the public, mankind, if you will?
Okay, let's talk about a couple of telephone calls we had about the 4,000. The way I had things organized, I had a very small company. We never had more than 13 employees, and my wife worked at home. She had a home office there. If you dialed our 800 number,
She
answered it, and then she, could handle quite a bit of those calls herself, or she could forward the call to one of the big players in there, me, John, and Greg, and let us handle it. I'm trying to think where that came from. Oh yeah, she had a telephone call from a hospital in a small town in Alaska, and that guy told her that at that little bitty hospital they had there, they had avoided buying a co-oximeter. They did not ever want to fool with one. They were too complicated, and it took a lot of maintenance and all. And he was interested in maybe buying ours that was this size.
The 1,000.
Well, she wanted a 4,000, all four.
But the small device.
And then he went on to say, what has happened a few times is when the weather gets cold, we have patients showing up at the hospital. They have these flu-like symptoms, and the physicians, investigate what they thought might happen or what's going on, and they don't have fever, and it doesn't seem too threatening or anything. So we just send them home, so they stay warm and get some rest. But then we do take a blood sample and we send it to a bigger town not far from here. They've got a hospital that has a co-oximeter. And we find out that we were sending them home for more carbon monoxide poisoning.
Ah.
Yeah. She handled that call. Now, the one
a great benefit for society.
And that we don't know how many times that kind of thing went on, but the fact that is so small and portable and easy to use makes a difference between whether any co-oximeter is used or not. Now, the other phone call I thought I would mention to you, she didn't know how to handle that one. She sent that one on to me. And it was from a physician saying, I've got a young woman here who is in danger of dying. And what I wish I could do would be to give her a blood transfusion, but her parents will not let me because of religious reasons. Now, do you know about perfluoride emulsion? And I said, no, I don't think I do. And he said, well, it's a compound that exists in tiny microscopic droplets, and they're so small that they'll flow through your arteries. And so I could give her a transfusion of this stuff, and because oxygen is very soluble in it, I could then increase the oxygen concentration in the air she's breathing, and I might be able to get her through this terrible episode. He said, but those little tiny droplets of what I call it, perfluoride, they scatter light. And I'm worried that I couldn't use the readings on your instrument. I know it messes up some of my big co-oximeters. And I had to say, well, I'm fairly confident that our instrument will give you the correct readings, but I don't have any proof of that. Good luck. She died. Yeah.
So it really did retract all the
in spite of all of the scattering that those little microscopic droplets caused, our instrument corrected for the light scattering and still gave you the right reading.
Got it.
Now, what that ended up doing was getting me interested in some of the clinical problems like that. So one of the next things Steinke and I did was write a paper about perfluoride emulsion, the fact that it worked in our instruments, but it didn't in these others. We published that, in a peer-reviewed journal.
Well, and so now you've attracted enough attention that the company is beginning to look like it would serve the broader interests of a buyer. When did you begin to think that maybe it was time to start monetizing your invention and passing it on to another owner?
It never occurred to me.
Someone called one day?
Well, the The difference between the avoximeter 1000E and the 4000 was this went into the cath labs, and we could sell it with direct mail advertising. That was a target you could aim right at. And in fact, a woman who had helped me when I was editing the American Journal of Physiology, they gave you money to pay a half-time secretary when you had these paper manuscripts.
Right.
When I was no longer a member of the editorial thing for the journal, she came in one day and said, "What's this about you having a company? You never told me." And I told her what it was all about. She wanted to go to work for me. I said, "Well, Adelaide, I don't think I have money to pay you." She said, "Oh, I work for nothing. You don't have to worry about that."
The right kind of employee.
And so all I had to do was to buy her the hospital blue book, which lists every hospital in America, and tell her, look up every hospital that says they have a cath lab, and then call them up and get the name and address of the person who's running it. And there's usually a physician who's there in name only. It's some technician who's actually running it and buying the supplies and all. And so I bought her a new Mac and a printer and all that stuff, and she came up with the list of all the cardiac cath labs in the U.S., and that's what kept us in business. So when the NIH Small Business Innovative Research Grants, SBIR grants, when it ran out, we were already profitable. We put that one on the market, I think, in January of '93, and by the end of the year, we were already making a profit, and I could pay Adelaide and my wife both. We worked for nothing all year.
And yourself, I hope. So when did you sell the company and why?
All right, that I have to look up. One of the things that we did was when we came out with the Avoximeter 4000, we found out we couldn't give it away. You really had to have a big company that had a sales force, that had people going to hospitals and going to the people in various locations, in order to sell something. We couldn't do it. And so we approached several different companies. Some of those worked out real well. For example, Instrumentation Laboratory in the Boston area. They were the company that invented the first co-oximeter, the one that ruptured the red cells and all. And they licensed our technology, put it into a big instrument that was having R&D done in Italy, and they got that big instrument going that included ours. So when we received royalties at the company, we turned half of those royalties over to the university. So that was one of the things that worked out well for us. Now
for the university.
Oh yeah, the university was getting theirs. We tried several other companies, including a big company, and it didn't go well. For example, the big company would go to a hospital and sell them some of their stuff, and the order would include one of the Avoximeter 4000s, or maybe two or three of them. Well, we wouldn't hear anything about it, and a month or two would go by, and the hospital would call us up, and they'd be all upset. They placed this order months ago, and they never got it. We weren't informed by the company that they were doing it. Well, I don't put up with that.
No.
I didn't care how big a company they were. I cut that off. Now, in the case of Instrumentation Laboratory in the Boston area, that was the guy who was one of the inventors of the very first co-oximeter. He and I trusted each other and everything. And when he had the authority to take on the Avoximeter 4000, he said, "I'll tell you what I'll do, Pete. I'll sell it, but it can't have your name on it. It can't be that color.
Oh, so you changed the name.
It's got to be a color consistent with our other products, and it's got to be called the Gem Opal." Well, if you look at their website, they're still selling the Gem Opal.
But it's this technology.
But now to get back to your question, we sold the company in 2006. Now, at that time, we sold it to a company called International Technidyne Corp., ITC, and they later were bought or reorganized or something. And now a company called Acriva Diagnostics in San Diego is manufacturing this one and the 4000, and they're still selling them, And we know that because they're still paying royalties.
And the university is getting royalties, and I assume you and Chuck are still getting royalties.
John Steinke.
John.
Well, John is deceased now, but his family is getting his royalties now.
So, Professor Dr. Shepard, what advice do you have for entrepreneurs in this area?
Well, it may be pretty obvious. I gave a talk for the Inventors Club in San Antonio a long time ago, and I told them that sometimes recognizing an opportunity is easier than exploiting it. Sometimes it's the other way around. Now, the other thing I told them was if you fail to achieve the goal you're seeking, you can aim higher and try harder. But if you're lucky, you'll fail to get what you were after, and something even better comes along that you didn't anticipate. And that has happened many times throughout my career.
Good advice to end on. Dr. Shepard, thank you for sharing your experiences, your journey toward invention and entrepreneurship with us.
Thank you.